what I find is a good place to start, because it allows me to bring in a bit of a gray area that I need to express to you. So let's do the barbell problem like we were trying to do yesterday. And this time we're going to put some numbers to it, because I think the only way for you to see this is with some kind of expression. So that's not going to work. Let me do that a little bit better. All right. So I put the barbell with the kind of the rod portion showing. So I wanted you to kind of see that I'm trying to put the spherical parts so that their center is where the end of the rod is. Does that make sense? Because when we talk about like the moment of inertia of the spheres, it's going to be from their center of mass to where the axis of rotation is. So I want their center of mass to be kind of right there. I don't want to have to add something to like the length of the rod, like to include its radius or something. That's why I'm putting it like this. But let's consider that these have a radius of, say, 20 centimeters. And let's make everything the same mass, 2 kilograms. And let's make this length, say, 1.5 meters. And we'll do the same thing over here where this is 20 centimeters. And I really think that's about it. Oh, let's make the mass of the rod 2 kilograms too. There. I'd like to, you guys, we talked about the parallel axis theorem yesterday, right? With all the information that's here, could you calculate the moment of inertia of this system, say if I wanted to rotate it about its center? Do you think with what you did yesterday you could do so? I'm going to put some things up here I'd like to see you try first, because I think some of you can't. I think some of you will do okay. So let me remind you that the parallel axis theorem requires that we take the moment of inertia about the center of mass and add a shift distance. Do you remember that? That was the parallel axis theorem. So we're dealing with the moment of inertia of a sphere, 2/5 mr squared. So can you find both of these separately for me? And while you're doing that, this is just a rod spun about its center. That's 1/12 ml squared. I think I've given you 3 things to calculate, maybe 4. So find this, and find this, and then we'll talk. I'll give you 30 seconds, and I'll pick 3 of you. Goku, give me one of them.
0.375.
You want to help me with where that is? I'm pretty sure that's that, right? The units are kilograms, meters squared. Is that good? All right, let me see. Let's switch tables here. So how about Ethan, can you give me another one? That was a big Is that going to be a no? Yeah, let's be a better participant. There, I took one for the team. We good? What you guys got? Excellent. So, but my goal wasn't to have to jump in there. So, Sophia, can you give me one? Or whatever one's left? There's only one left. You think it's 1.25?
Yeah. Let me read it.
I think it's 1.125. Yeah, that's what I thought. Now, I'm kind of leaving them spaced out on purpose. And again, a reminder, kilogram meter squared. This will be the combined momentum of the sphere when spun about this location. Correct? And although that's a little messy, let me clean up my own handwriting some, just so we are all together. Because I want to point something out that you might not see on your own. First, this is the sphere by itself, right? It's tiny because its radius is small. This is what the sphere becomes when we start rotating that far away from its center. Do you see how much bigger it gets? There's a gray area over here I want to talk to you about. the parallel axis theorem suggests something, and it probably is something that we should pay attention to. The moment of inertia about the center of mass is probably the smallest moment of inertia for the object. Because if I shift it to any place else, I am adding something to it. Agreed? I mean, it's pretty clear. I'm going to be adding something. Whatever that shift is, it's going to be adding to the moment of inertia. Once I start getting outside the size of the object, whether that be something circular, the plank, doesn't really matter. Once I start getting outside the size of the object, this term is bigger than this term. Right? Automatically. Because once I'm outside the object, that value for x is going to be bigger than r. And that value for L is going to be bigger than L. Do you realize it doesn't take long before this is overpowering the number? I mean, look at it already. We just moved it a small distance. And already this number is 2 orders of magnitude bigger, right? 50 times the size. It has 50 times more inertia. It's like this part doesn't even exist. So when do you not have to calculate that? Do you understand what I'm saying? When is this part? This part is already down to the 3rd significant figure, which you guys only care about is if it's a 0.4 and you want a 0.5. That's when you care about your 3rd significant figure, right? Grades. I have an 89.4, Mr. Shelton. Can you help me? It's only the 3rd significant place. When does it matter? Apparently it matters for grades. Would you agree? Sorry to bring it back home to grades, but you guys ask me about those things all the time. But I want to point out something. I don't know that it matters that much. So there's a gray area here. When do we reach the point where we're outside far enough where I don't have to use this and can only use this? It's not definitive. And I don't want to say you can use it when this is the case. But this is known as the point mass formula. We'll use point mass formulas whenever we feel as though we don't have to worry about the object's shape. It's when the shape of the object no longer really influences its moment of inertia, because most of its mass is well outside the axis of rotation. There are subtle times when it's going to be obvious, like when they don't tell you the shape of an object. Imagine a merry-go-round, and a kid jumps on the merry-go-round. Well, the merry-go-round's got its own moment of inertia. But if a kid jumps on it, what shape are they? Some kind of blob? I mean, if I tell you where they are on the merry-go-round, it's probably going to be spinning outside their axis of rotation. Right? They're going to be on the edge of the merry-go-round. The axis of rotation is at the middle. So I'd argue that there's often times when you don't have to know the shape of the object. Now, there's nothing definitive here, but if they don't tell you the size of the object, only its mass, you could probably use this. Right? If they don't tell you the shape of the object, only its mass, you can probably use this. Everybody got it? Again, it's a gray area. If they give you the shape of the object, you're probably going to have to use the shape of the object. But if they don't, treat it like a point mass. When we do orbits, all the planets are just point masses. It doesn't matter how big they are. The axis of rotation is well outside their mass. So ultimately, you treat something like a point mass when the axis of rotation makes their actual shape not matter. But I want the shape to matter for this one because this is an exercise. So we have found the moment of inertia of the sphere based on an axis of rotation at the center of the rod. We're mounting it to the end, so we add these two things together and we get 1.157 kilograms meters squared. Now, we're almost done, but we haven't even talked about this sphere. Do we have to? Like, do I have to work it out separate for that sphere? Do you understand there's enough symmetry here where I probably don't have to? And does it matter that it's on the other side? Do I have to do anything special about being on the other side? Nope. Moment of inertia is not a vector quantity. It doesn't matter on which side it is. R might even be a vector, but to be honest with you, you square all of those numbers. So any vector information would be gone. So all we got to do is say, all right, this times 2. That's the total moment of inertia. So I want the total moment of inertia. It would be the 0.375 plus 2 times 1.157. And notice this term is really just overpowering the whole thing, isn't it? Just overpowering the whole thing. Those spheres being on the end, they're the same mass as the rod. Those spheres make an amazing difference on how much inertia this system has. Yeah, so all you do is add it up. That gives you the total moment of inertia. All right. We've talked a lot about moment of inertia today. You understand that I think I've given you everything you need to know for any kind of problem that involves a combined moment of inertia. But my history with you is that you'll say that I'm wrong. So because you'll say that I'm wrong, I'm going to see if you can do something. Because this is one of your problems in your homework. All right, let's say this has a mass M and radius r. And let's say this rod is mass M and its length is 2r. And we're going to rotate this about the center and treat it like a pulley. We're going to combine these two objects into one object. And this object will have a mass of 2m, right? The rod is m and the hoop is m. So the object's mass is 2m. But what is the moment of inertia of this object? Now, 5th period, I held their hand the whole time. Can you do it? Let's see. Is there anybody who'd like me to go over where I got 4/3 mr squared? Well, first, it's a hoop, right? With radius r. So its moment of inertia, just the hoop portion, is mr squared. The rod is fused to it, and the moment of inertia of the rod is 1/12 m times its total length, which is 2r squared. So that makes it 4/3 mr squared, which is 1/3 mr squared. So when I add these two together, it's 1 plus 1/3, which is 4/3. So 4/3 mr squared. We all good? That's a lot of arithmetic, but it's luckily 3rd grade arithmetic, so we're okay. Now, let's say we apply a force to it here with tension T. In fact, we'll say T1. And somebody else applies a force to it here with tension T2. So 2 forces being applied. Under the action of these forces, do you think these forces will constitute torque? Are these forces being applied in such a way that they would cause a torque to the hoop? Looks like it to me, right? The force is applied at some distance away from the pivot point and at an angle that is reasonably good for providing torque. In fact, any string would come off of a round object at a tangent, unless it was glued on to the edge of that round object. So when we wrap strings around pulleys and stuff, they always apply forces perpendicular to the torque arm, always. So you never have to worry about it for a round object. So in the case of these two, I'm going to establish that there is a net torque problem, and it's going to equal I alpha. I'm not so much interested in the results of this. What I'm trying to impress upon you is that from now on, our problems have a level of complication. With net force problems, we added up all the forces, dealt with their direction maybe, but that was the extent of it. In the case of this problem, we're still going to have to add up all the torques, but we have 2 torques. Dealing with them requires that we deal with more things just to get what the expression for the torque would be. Do you see that all right? Now I'm expecting that this torque is probably negative and this torque is positive. I don't have to choose it that way. I'm just picking something because I need to pick a direction to make positive. And one of these torques is causing it to be clockwise, and one of these torques is causing it to be counterclockwise. So make one negative and make one positive. From there, well, that's going to be torque arm distance is R, size of the force, T2, sine 90 degrees. None of this new, right? We've talked about this. So next one, R, T1, sine 90 degrees. So this part about doing net torque is going to be more complicated because there's lots of pieces associated with dealing with torque. Moment of inertia isn't necessarily just some formula that we grab. We might have to do something complicated to deal with the shape and size of the object. So dealing with the moment of inertia might be complex. And when we're done, all that Newton's laws can do is generate a relationship that might be able to be used to solve your problem. That's what we've done here. We've generated a relationship that might be able to be used to solve our problem. I'll point out a lot of things about this. For one, the R's. It's just nice that this one, that all the R's end up being the same value, right? The strings are around the outside edge of the pulley. That's convenient. That's not true over there, right? Because the sprocket in the middle has one radius, but anything I stack on top of it has a different shape and size. So we don't have to have it so convenient. But this one's kind of convenient. I think one of the R's might cancel out. Do you see why? I see why. So I have 7 minutes left, which is not as much as I would really like right now. So I don't want to spend too much time setting this up. So let's cut to what I hope is a very straightforward example, but one that is now within our capabilities to assess. So I've got, and let's just make everything in reasonable terms for this to go quickly and smoothly. From now on, let's deal with the fact that we might have pulleys that are no longer massless, but are massive pulleys. They have inertia. Because they have inertia, they need to be factored in. There are 3 objects in this problem. If we assume for this example that there's no friction, and let's give this a mass of 3m, let's give this a mass of m, and let's say that this is a disk of mass m and radius r. I want to find the acceleration of this system. Now, before I go any further, you guys are reasonable people, but you're sometimes not always, there's a failure of imagination, and that's what a teacher's supposed to be here to do, to provide you with context. The disk. If the string doesn't slip with respect to the disk, then the disk is going to spin. Would you agree? What direction is the disk likely to spin? Clockwise or counterclockwise based on this arrangement? Clockwise. I agree. I think the whole system is going to have acceleration in that direction, right? Would you agree that the disk is going to accelerate? Okay. The only way the disk can accelerate is if the net torque on it is not 0. Right? That's the only way it can accelerate. There are 3 forces acting on the pulley. Do you see them all? Let's make sure. There's a force this way. There is a force this way. And there is a force this way. Right? Because is the pulley going to go anywhere? I expect it to stay right there. I think the net force on the pulley is 0. But one of those forces doesn't apply a torque, does it? Of those forces, 1, 2, 3, which one doesn't apply a torque? Why? The way you would say it is that the force is applied at the axis of rotation, right? That force is applied at the center, so the torque arm's 0. That's why that force doesn't apply a torque. Now, if we eliminate that force from our conversation and only talk about these two forces, one of them has to be bigger than the other. Do you see why? If not, I'll make it clear. This one has to be bigger than this one so that the torque is unbalanced. See, when the pulleys were massless, that didn't have to be true because there didn't have to be an unbalanced torque on the pulley. But the moment the pulleys have mass, those two tensions are not the same any longer. So this becomes T2 and this becomes T1. That also means that T1 acts on this box, but T2 acts on this box. You follow what I'm saying? We no longer have this one force easily canceling out. But that doesn't change the role of the problem. The problem's still going to be the same. I'm still going to have, say, mg minus T2 equals ma. That's still going to be true. And I'm still going to have T1 equals 3m times a. You see where I got that from? I'm still going to suggest that those two a's are the same, as long as the string doesn't break or stretch or anything like that. However, two torques, right? And I'm making into the board positive. So I think RT2, which would be the torque from T2 on the pulley. Go ahead. I'm trying to go through this. Do you see why RT2 is the torque in one direction on the pulley? I'm ignoring the sign because we know the sign has to be 90 degrees. And I'm going to say RT1 is the other torque acting on the pulley in the opposite direction. Any questions? I'm not making a long chart of torque 1, torque 2, whatever. I'm just going to do it this way if I can. But this is going to equal I alpha. Now, would you agree that alpha and A are going to be related? I think so too. In fact, if the string doesn't slip, wouldn't A have to be related to alpha like this? If the string doesn't slip, right, the amount the pulley turns would be directly related to how much each mass moves. Right? If the pulley made one rotation, wouldn't the box go down one circumference and the box on the table go over one circumference? If that's true, then that must link the velocities, the accelerations, and the displacements. Go ahead. Now, you guys are smart. I know you're packing up, but we're going to replace alpha, right, to get everything in terms of A. And we have an R over here too, right? And this is going to have something with R squared in it. I bet it's going to be like 1/2 mr squared. It's a pulley, a disc. Do you see that there's a possibility that the R's might cancel out? 3 equations, 3 unknowns. T1, T2, and A. You should finish this problem. Try and get an expression for A. I'm going to finish it between classes and post it, but you should try it. And to finish it between classes, I do some substitution here. RT2 minus RT1 equals 1/2 mr squared times A over R. So I'll point out that all the R's cancel. Yep, leaving me with T2 minus T1 equals 1/2 ma. Go ahead.